So last time we did about light, and this time we're going to do more on light. We're going to start doing the classical optics. So the first chapter's on, I'm sorry, this is giving me a hard time. So the first chapter, yeah, there it is. The first chapter is on, the nature of light. So what we say is big ideas. Okay, big ideas about the nature of light. Energy is, in a photon, depends upon its colour. The speed of light is a constant in a vacuum. It changes if you go into different media. Reflective surfaces are specular or diffuse, and specular reflectors obey a thing called law of reflection. This is not complete. There's also the law of refraction, and there's things like total internal reflection and the critical angle and the like, and we're going to go through some of that. Big argument back in the day about what light was. There were people like Newton who thought of it in terms of particles like little bullets, and they were the so-called corpuscular theory people. And then there were people like Huygens who thought of it as a wave. And there was evidence for both sides. And I guess the danger, the thing that they did that was a little bit unwise, was they thought of it in terms of either or. They didn't think of it in terms of, it could be a bit of both. They thought about it in terms of either or. And so my visualization of it is that it's a little ravioli kind of thing with light inside. It's a little package, like an envelope. It has a vague beginning and a vague end. And so it's somewhat localized, but it's a wave. So it's and what we get, the difference between one photon and another, is that we have different color of light, and we link color with frequency. We don't link it with wavelength. Very often, when you see these charts, they will have light color expressed in terms of wavelength. And that works fine if you're in one given medium, like you're in vacuum, then that works fine. But if you change the medium that the light is in, the colour will not change, but the wavelength will. And I think it's just unfortunate that we tend to talk backwards and forwards about wavelengths of light for different colours, when really we should link it with frequency of light for different colours, because it's the frequency that doesn't change. So my visualization of the blue light is it's a high frequency oscillation, electromagnetic oscillation, and for red light it's a low frequency electromagnetic oscillation. And we can go beyond there. We can go redder than red, which is basically radio waves, and we can go bluer than blue, and we end up at gamma rays. What's not so obvious, and certainly wasn't obvious until Planck came along, and that is the fact that the actual amount of energy contained in a photon depends upon its frequency. That's not so obvious. And so we have this very standard equation, E equals HF. Sometimes they'll use mu instead of F, but that's just the textbook. The E equals HF, the energy equals Planck's constant times the frequency. And we can see that Planck's constant, 6.6 times 10 to the minus 34 joule seconds. So that's like that's a very small amount of energy. So if I have something like 10 to the 6 for my frequency, then I would get some astronomical small bit like 10 to the minus 28 joules in that photon of light. This means that a blue photon has more energy than a red photon. Now, it's interesting actually. Blue photons come from very high temperature objects. Remember what we said, EM radiation comes when you get charged particles to oscillate, to accelerate basically. I can get light out if I get charged particles to go in a circle. That's a synchrotron. And I can get very high frequencies, and I can get, basically X-rays and whatever I like out of that. I can get light to come out when I oscillate charged particles backwards and forwards. in a wire, like we do in microwave towers or we do in standard radio towers. I can get it from heat. If I heat something up, it will start glowing red. That's because the charged particles are so hot that, and I can see that electromagnetic radiation. Why can't I see, if I turn all the lights out, why can't I see a colour associated with the inside of a cave or the inside of a darkened room? And that's because I have developed eyes that are not sensitive to those colours. We decided biologically to develop eyes that were sensitive to the colours emitted by our sun. And we have a sun which is about 5,000 to 6,000 degrees. So we see a range of colours, the rainbow of colours if you like, that are emitted by that kind of body. And so we said we'll give up on the night. We won't look for infrared. We won't look for things like that. We'll just look for the visible spectrum because that's what's going to be dominant during the day. And at night we'll hide. So we basically sleep at night, etc. Very small part of a very big electromagnetic spectrum. How does photon energy relate to frequency? So we say E is equal to HF. So I guess that would be a linear relationship, wouldn't it be? If I said plot me energy versus frequency, you would have a straight line. And that straight line, the slope equals H. What is the energy of a green photon? Actually, I think that's more like a blue photon. I was so proud of myself because I remembered the wavelength of a photon, and it turned out I remembered it wrong. I think it's a blue photon. And again, with this little cadre that, yeah, this is that many nanometers. This is assumed to be in vacuum. As we'll see pretty soon, if it's going through glass, it will have a different wavelength. But what I'm doing here is I'm saying, well, let's have a look. We know that lambda is equal to 400 times 10 to the minus 9 meters. And I want to find my energy. And the equation I have is that E is equal to HF. Well, that's not going to do it. Oh, yeah, I remember. V is equal to F lambda, or what we say for light is C is equal to F lambda, because that's the speed of light. And so we combine these guys together and we get E is equal to H, and rather than F, we're going to put down C over lambda. So E is equal to H. We'll leave H alone, and then we'll go C 3 times 10 to the 8. I expect you to know C, so just make sure you know it. And then lambda in this is 400 times 10 to the minus 9. So E is equal to, I don't know, whatever that works out to be. Let's have a look. 3 second EE to the 8 divided by, and then we'll have 400 second EE to the minus 9. And that's going to be 7.5. 7.5 times 10 to the 17 H. So let's actually, just for the fun of it, multiply that by Planck's constant. 6.63 times 10 to the negative 30. So that's times 6.63 second EE to the minus 34. And that's going to be, let's go the right way. That's going to be 4.9 times 10 to the minus 19. And that's going to be in joules, standard SI units. 4.9? Yep. Now I can talk about energy also in EVs, electron volts. And it turns out that in modern physics, you often talk about energy in EVs because you're accelerating a particle, usually with a charge like an electron, to a certain voltage. Okay. So, yes?
So on a test, would you rather put it with H not factored in?
Yeah, I don't particularly want you to learn the constants. If you do, I'm fine with it.
I
I'm happy we leave it. I don't like you leaving things like pi's in there, because pi's are readily accessible to us. And I certainly don't want 2 square root of 17 left in there. And then somebody else tries to work it out, and they make a slip and you didn't, and what do I do then? Do I ignore the slip? The slip's a slip. What do I do? If someone's always making slips, it's a real problem. So I want you to numerically work things out, apart from for constants like this. So if I want to work this out in electron volts, I say my energy in electron volts basically equals my energy in joules divided by the charge of an electron. So I'm going to take this, I'm going to divide it by 1.6 second e to the minus 19, and that should be about 3 electron volts. Something like that. So it's about the same. So it's not a big deal, but get used to kind of changing things backwards and forwards. Not much energy in a photon, but more than there would be in a red photon. Okay. So that's real modern, actually. What we just did is real modern. It's probably last century, 100 years old. Well, light's difficult to work with. You use it to see, but you can't see it. You can see when it's absorbed. You see the effects of it absorbed on the retina, but you can't see a light photon going by. So it's kind of a very weird thing. We're at that stage where we're looking at stuff which is unobservable, even though we use it to observe. It's the strangest thing. So it's not surprising that we're only finding out about these things in the last 100 years or so. Ironically, though, they actually were able to figure out the speed of light a lot earlier than I think I certainly guessed, and I think a lot earlier than what a lot of people would have guessed. First of all, they knew there was some issue between light and sound, simply because, back in the day, they'd have battles taking place in a very confined space like a battlefield, and the generals, to avoid being shot, would be on a hill watching. So I want to be a general rather than a person fighting. And you see the cannon's red flare. Is that the right terminology? I can't remember.
Yeah, it's fine.
The cannon's red flare, and you didn't hear anything. And then a bit later you heard the sound coming. So there was a delay between light and sound. So people figured out it takes a while for sound to get places. If you go into a valley and you shout on an echo, hello, comes back. That's because the sound has gone from you and bounced off a mountain range and come back. And if you go into a long hallway, it's a bit sad about this building actually. If you go into certainly a school hallway, I don't know if your physics teachers did it with you, but you can take the class outside and you stand in the hallway and you clap, and you can hear the echo coming back even in a typical hallway. You can hear it because sound travels relatively slow. Light appears to get there. Well, how do you tell? But you think light gets there instantaneously. It gets there so quick you can't kind of like sort it out. I think it was Newton who had the idea that light must have a finite speed, and so he had the idea about shining a lamp onto a mirror and timing it. Or it might have been Galileo, one or the other of them. And of course, what happens is the human reaction time is much slower than the actual time taken, so you can't get any decent readings out of it. So fast, it's, how can you get a fast enough clock? And you might be tempted to give up, but of course the thing about speed is you need really long distances to make the time interval long enough. And if you think about it, in about 1608, Galileo took the spyglass, which had just been developed in Holland, and made it much improved. So improved that one of his friends said, "This is not a spyglass, this is a telescope." We used to, and that's where the term came from. So in 1608 or so, Galileo invented the telescope, and immediately, within days, used it to look at the moon and then the stars, and etc. one of the shocking things about a telescope is that when you look at stars, they don't get any bigger. You don't magnify the stars, you magnify the distance between the stars. Because it's so small, it's beyond the resolution of the telescope, just like it's beyond the resolution of your eyes. And what makes the star appear to have some size to it is actually the optics in your eye. It's not the star. You can't discern the edges of a star. You can planets, and that's why planets look bigger, you know. Now the stars look brighter. So telescopes, one of the confusing things is that people think telescopes are about magnification. And so you buy your kid this little plasticky telescope from some science store, well, some store, and you take it home and it is awful. And it says 300 times red, 300 times X, and you go, whoa, you see everything on the moon, and you look at this thing and it's shaking all over the place. And your kid is, you know, completely disappointed, and it's a total fail. And because it's not about resolution. What it's about is light gathering, really. So then you go and you buy yourself, just if you're interested, you buy yourself a telescope. There's a good one made by Orion Telescopes, which costs like $60. It's a 3-inch reflector. It comes with 2 eyepieces and a little LED sight. The 2 eyepieces cost more than $60. And it's a little tabletop mount. And you do what I did. You buy it. You're not expecting that much. You look at the moon and you go, wow, that's really cool. And then you look at Jupiter like Galileo did, and then after him Roma did, and you go, wow, because you can so clearly see the presence of the moons of Jupiter. You can't discern them. You can't see them as spots. You see them as you can't resolve them to make them structure, to get structure, but you can clearly see them. And Galileo thought that the 4 moons of Jupiter were in fact stars, but because he looked regularly and because he kept good notes in his logbook, he basically saw that they were moving and realized, oh my word, no, they're stars that are moving around this planet. They are moons of that planet. And that was totally revolutionary, because according to the status quo, the dogma of the day, everything revolved around the sun, around the earth, everything, not around anything else. The moon went around the earth, the sun went around the earth, everything went around the earth, and yet here's these moons clearly going around Jupiter. So that said that the dogma of the day was just that. It was just, you know, rules. It was not necessarily true. It was just rules. He also did then he did a very slick thing. He was being sponsored by the Medici family. They were the people who were bankrolling him. So he named the moons after the family. Kind of like, hey, I named something new in the heavens after you. It turns out that we threw away those names. It was like too commercial, or maybe we weren't being paid by the Medici family, so we gave them our own names. But yeah, he named them, and it's quite ironic because you get to, if you discover something, you get to name it. And he certainly discovered this, you know? And yeah, he did get to name it. It's kind of interesting. And then, but to complete that story, so then the next thing he did was he looked at Venus. Venus is so close to the sun in terms of angles that you tend to see it just before dawn or just after sunset. And it's what people call the wishing star. It's not really the star. It's the first star you see at night. No, it's the planet that you see at night. It's much brighter than any star. So it's hard to observe beyond that because actually Mercury is really the hard one to observe. But Venus is somewhat hard to observe before that because it's very often during a bright sky, and you know, it's very often close to the sun. So And what he noticed with that was that when he looked at Venus, it had phases just like the moon has phases. And he was able to show that Venus, or observe that Venus had a full moon phase. And the only way you can get that is if Venus is on the opposite side of the sun, as opposed to our side of the sun. And that was clear evidence that Venus was going around the sun, not around us. And that really was revolutionary in its nature. Okay, so that happened in 1608, and then what's this? This is like 65 years later, so it's basically a couple of generations later. They've been observing Jupiter's moons. Let's consider Io one of the moons. And they found that there's a time it takes to go around. And you can measure it quite precisely by saying, when does it go into eclipse? When does this thing disappear behind? From the right. And then you put down a clock and then you time it until it disappears from the right again. So you do that. And what they found is that although on average it takes about 42.5 hours, it's not always 42.5 hours. That's the average value. So we say that Ole Roma observed Io, a moon of Jupiter. Io should go into eclipse every 42.5 hours. Roma found that Io's periods were shorter when the Earth approached Jupiter and longer when the Earth receded from Jupiter. So let's just try and figure this out. So we're looking at the Earth, and we're saying the Earth is approaching. And what happens is that the moon goes into eclipse, and that signal takes a time to get to where the Earth is. And then, as far as the moon is concerned, 42.5 hours later, it does it again and sends out a second light signal. Yeah, basically. Sending out a light signal just means sunlight reflects off it. And so the second signal comes out. But by then, the Earth has moved. And the Earth, I'm going to exaggerate, but the Earth is now here. So the first signal took longer to get to the Earth than the second signal did. And so I'm going to draw this kind of at the bottom. So if Io is really doing that, let's say there's a time axis, and I'm indicating the clicks when it goes into eclipse. So every 42.5 hours it goes into eclipse. There's a delay, and the delay before we see it for the first one is longer than it is for the second one, because we're further away. It's further away for the first time we see it than it is for the second time we see it when the Earth is approaching. So what happens is I'm going to draw this downwards. So can you see how this is less than 42 hours? And if we go the other way, we say, okay, so now we send out the signal when it's here, but the second signal goes when the Earth is further away. What happens now is the delay is shorter on the first journey because we're closer, and the delay is longer on the second journey because we're further away. So this now appears to be longer than 42.5 hours. Now, if you can figure that out, and then you can take into account the geometry, like the Earth's diameter, the orbit of the Earth's diameter, and the like, you can figure out how fast it has to travel to give that delay that you're measuring. It's kind of very clever. So basically, Roma found Io's periods were shorter when the Earth was approaching and longer when the Earth was receding. Roma used this observation to calculate the speed of light was 2.1 times 10 to the 8 meters per second. It's within a factor of 10 in lab. I'd be very happy about that, you know. But he was wrong, and he was wrong not because of anything he did, actually. He was wrong because the quoted figure for the diameter of the Earth's orbit around the sun was wrong at the time. And if you take his work and you put in the correct number, he would have been almost exactly right. It's a very solid way that he came up with. It's very good. And so this Danish guy, there's a stamp, commemorating him. Have you noticed how he looks like Newton on some level? They all kind of look that. It's all the hair. You just see the long hair and all that. It was so funny being a physics student. In my generation, long hair was like it. And, my dad's generation was short hair and military. And my dad's generation was, who do you think you are? And you'd go, Newton! Which they didn't get because they didn't do science. But speed of light. Then look at Fizeau, French guy. I think French anyway. Fizeau basically measured speed of light using basically the most straightforward method. You shine a light and you see how long it takes to come back again. So you have a mirror across a field and you shine the light. Now, okay, I'll just go through it. So basically the speed is going to be the distance to and from the mirror. So it's 2 times the distance to the mirror divided by the time taken. And so the problem is it's timing, isn't it? How do you time precisely? And a very clever technique. You take a wheel and you put holes in it or you put teeth in it, and you use the wheel to chop the light going. So you mainly have the light beam blocked, but when the slit comes in front of the light beam, suddenly a beam of light is allowed out. And it hits the mirror, and it comes back, and it hits the next tooth, because the wheel's not going fast enough. So you don't see anything. You see the light going out, but not coming back. You speed up the wheel. It goes out, comes back, and it hits the middle of the next tooth. That's progress. It goes out, hits, and it eats 3/4 of the way through the next tooth because you're going faster. And finally it goes out and it comes back through the next tooth. Now you see the light coming back. So you spin this thing up and you don't see any light coming back, and then when you're at the right speed, you see the light coming back. And so you can do the math based on that. So we say tooth wheel, chop the light going to the mirror, same speed, same wheel chops the light on the way back. Rotation speed of the wheel was adjusted until light went to the mirror through one gap and came back through the next gap. And he found 3.1 times 10⁸ meters per second. In Fizeau's experiment, the distance from the toothed wheel to the mirror is 1 kilometer. So here's our wheel and here's our mirror. And this is 1 kilometer from there to there. And the wheel has 100 teeth. I'm not going to draw 100, but it's got 100 teeth. And number of revolutions, 400 rev per second. So you can spin quite quickly, and then when you put teeth in it, you get even smaller divisions of time. It's really quite clever. And so we say that our speed is equal to 2d over t, which equals 2 times 1,000. And now we've got to figure out our time. If this had 1 gap per wheel, then it's 1 over 400th of a second. It's 1 over 400 seconds for that tooth to come around, for that gap to come around. Agreed? If I'm going at 2 revolutions per second, it's 1 over 2. If I'm doing 5 revolutions per second, it's 1 over 5, 1/5 of a second. It's going to come round again, yeah? If I'm doing 10 revolutions per second, it comes round 10 times in a second, so it's 1/10 of a second. 20 revolutions per second, it comes round every 20th of a second, so that's 1/20 of a second for the timing, agreed? So I take a second and I divide it by the number of revolutions per second, yeah? And now, all I got is not 1 tooth, I got 100 teeth. So it's going to be even shorter time, because, so I get multiply it by the number of teeth or the number of gaps on your wheel. Yeah? So we say, okay, C is equal to 2 times 1,000 over, now we've got to go 1 over 400 times 100. So that would be 2 times 1,000 times 400 times 100. So C would equal 2 fours are 8. 8 times 10 to the 3, 4, 5, 6, 7. 8 times 10 to the 7 meters per second. Now that's not the right answer because I'm making up the numbers, but that's the principle. I'm sorry?
Meters per second?
Speed of light, yeah, meters per second. Now the book, I got a little alarm bell going off. The book does it slightly differently. It's not that this is wrong or the book's wrong, it's that I think the information is slightly different. I just can't remember for the life of me how the book does it slightly differently. But I just can't remember. So I'll look back and sort it out. But this is the way I want you to do it. So the next thing is Newton. So Newton basically was a frighteningly bright person. And I don't know if I told you this, I hadn't seen you for a while, but basically Newton, born to a farming family in Lincolnshire. Did I take this? Born to a farming family in Lincolnshire. Dad died when he was young. Mum married again. Stepdad did not want kids. So Mum and Dad lived in the city, which is Grantham, which is hardly a city. It's not very big. And poor old Isaac got left on the farm, raised by, these people were not lords and ladies, but they had property and they had farm workers, basically indentured people. An awful lot of people in the day, they didn't have freedom of motion. They were basically living in property that was owned by the lord of the manor, and basically, kind of like he couldn't afford to leave. Actually, almost like an indentured servant, a serf, let's say. There were people to look after the boy, so they looked after the boy. And then, when the boy got to a certain age, they farmed him out to a teacher. So the teacher basically supported himself. This was before many schools. There might have been a couple of schools around, but they were for the aristocracy. So the way you got your kid educated is you basically sent them off to a school which was a family. And one of the people there was trained in classical studies, and basically you lived with a family. So his mum and dad moved back to the farm, and he moved in with his family. He was really bright. And so Cambridge was going at the time, and so was Oxford. And the way you got into Cambridge or Oxford was you were rich or you were really bright. And he was really bright. And so the college basically took him in, and the way he earned his keep was he basically was a runaround, a gopher for some of the fee-paying students. So he was so bright that when he graduated, one of the mathematics professors said, "I'm retiring. Give him my job." And they did. And that job still exists today. And my understanding is it's the title that Stephen Hawking has. So that position has gone down through 350 years, through person to person, most of whom we never heard about. But, we know Newton, and because it's our generation, we know Stephen Hawking, been known 350 years after after you do something is kind of amazing. Steve, he was a young guy. He was really smart. He basically got living expenses and a little bit of money and a room in the college, and he could live there and he could do his work there. Probably had to teach classes. I don't think that would have gone well for him. He used to avoid meeting people. He basically would go to the canteen, the refectory, at the very end and take his food back to his room. He didn't socialise at all. Story has he had no friends, none. No companion, no nothing. He had 10 years doing physics. He had 10 years doing alchemy. Not so good. He had 10 years communing with spirits. You know.
There's a New and Darkest Secrets, something like that. A book was written about it.
Oh, is that right? Okay.
Yeah. I had to write a paper about it.
Okay, good. So he was really enamored with a guy called Robert Hooke. And Robert Hooke was instrumental in getting the Royal Society off the ground. In Galileo's day, they had this idea that you just write to your friends. There's a community of educated people, you just write to them and, you share ideas. And the printing press was developed, and that enabled mass production of written words. You didn't have to go to the clergy, the church, because they had the scribes, or to the powerful, the kings and queens and the aristocracy to get stuff produced. You could just take it to a printer. So the Royal Society was based. The reason why it's called the Royal Society is because they went to the monarch in Britain and they said, "Give us some money. We got this idea." And the idea was, you pay us, and we'll set up this society. And basically, when people have scientific ideas, they'll write them, they'll send them to us. We will check them, we'll peer review them, and then, assuming it passed muster, or maybe with some modifications, we'll send it out to the community. And people will know what's been said, and then they'll be able to also do experiments. It was all evidence-based work. They will be able to do experiments and confirm or disagree, and by that way we'll make a very steady progress. And it works. With that methodology, you cannot have an important mistake for very long. You might change your model for something after a long time, but while ever the models that you use keep working, people will verify it or they will disagree, and if they disagree, they put a paper in saying, "I disagree." And that's the scientific process, and it works. And I guess the one big regret I have in my career is, for years, I've never really talked to students about the scientific process. And the result has been that I've not really done my bit to really drive home the fact that this process works. It's not that every scientist is right about everything every day. In fact, far from it. But what it means is, as a community, mistakes are found and rectified. It's not the quickest system in the world. But if you leave it alone and let it get on and you don't mess with it, it will make progress towards the truth. The truth being a model which works well for given observations. And it's based on evidence-based research. You do an experiment. Your opinion doesn't matter. Now, it's not the way that in modern days it's been portrayed, which is impartial scientists. That, ironically, that came after the Second World War, when they had the atomic explosions, when they had the atomic bombs. It petrified everybody. That's my dad's generation. My dad was, a young man when that happened, and he could not believe it. Just the fearsomeness of it, and the sudden change. And there was this realization of, oh my word, these people are dangerous. These scientists can do this. They can make something which can demolish a city in one go. This is, who's looking after them? And so you started getting all this stuff about the crazy scientists. So this popular fiction is almost like the psychology of the society. You can tell what people are scared about by look at their science fiction. Or you can tell what people look at their humor and you find out what they really believe, you know? It's what's on their mind is this stuff. And so you've got all these movies and books about crazy scientists doing crazy stuff. And I had a Russian student, when I worked at NC State, I had a Russian student come across, and he was straight after the wall had fallen down, and his family was quite well positioned in the Soviet hierarchy. He was a very well-educated Soviet, basically. And when he came across, he was asking me questions. It was clear that he couldn't believe that communism had failed and that capitalism had won. He was really, how can this be? He looked at us, you guys, you know, you're not superhuman. How can you do better than us? And one time I saw him, he came into work and he was laughing. And he goes, oh, I just saw, was it Dr. No, the Peter Sellers film? And he goes, we have the same thing in Russia, except it's all swapped around, you know. You're evil and we're good, and, you know, you have crazy people, and, you know, it's just amazing. So, so this idea of the impartial scientist is completely made up, and it was promoted by, you know, I suppose the government on some level, but it was picked up by the media. So Mr. Spock on Star Trek, you know, only the facts, very emotionally impartial and all that. Complete nonsense. Scientists are egotistical. They are, you know, most famous scientists walk into the room and they are determined that they will be the most intelligent person in the room. And they want that standing. And you'll be at meetings, and depending on which institution you work at, I worked at USF, and I would go in, and I was on a level with the people from UF and FSU and UCF. And when I moved here, I was at the same meetings, but you meet new people, and I was at HCC. I remember this person there were a crowd of us. I was talking with people I knew at the other universities, and he asked where we were from. And he literally just stepped in front of me and talked to the other two. It was the most amazing thing. And that ticked me off, you know, because, you know, I got an ego. And so this idea that scientists get in a room and collude to make stuff up is just, on the face of it, total nonsense. Now, there are powerful people in the community who will browbeat people, especially old guys and young people. You know, that's age old. And the young people have to kind of build their confidence and take on the old school. It's just generation after generation that has happened. And because the thing is, you're never going to get to be famous by saying me too. You can do every problem at the back of the textbook and get it right, and no one cares, you know? It's when you say something that's outrageous and you are right. That's when you get famous. I worked for a guy who was probably one of the smartest people I worked for. And he was well respected, but he wasn't famous. And I think the reason why he wasn't famous was because he never stuck with one area. He just would do the next important experiment. Boom, boom, boom. So he never got to the stage where he discovered anything that was like outrageous and, you know, earth-shattering and all that. He just did good work in a whole bunch of fields. He won't be famous. He'll be well respected in his community, but he won't be famous. To get famous, you've got to do something that's like outrageous and it's right. And that's what these guys did. Worry when science becomes media-driven. And that tends to happen more and more because, for nothing else, universities want kudos or standing from an important discovery. So what tends to happen is that when the university hears about some amazing discovery, rather than letting it go through the scientific process, they have a press conference and say, this is what we found. And then they end up with egg on their face because it wasn't quite what they thought it was, and it gets pulled back and all that. So to some extent, I worry when the media, when management gets involved in science. If you just let scientists do what they do, it's a slow process, but it works really well. And I get worried also when politics gets involved in science. It's kind of like you just got to let it go. And actually, or actually end up with bitter taste in your mouth. This is what happened to Newton, because Newton he really admired Hooke. And Hooke said, we got this Royal Society thing, send some of your work in. So he did. And it was sent out for peer review to these old guys who'd never done an experiment in their lives. And on the face of it, they ridiculed it and dismissed it. So now there's a problem. And kind of Hooke knew it, I think. Newton was sending in surprising stuff based on experiment, and it was been dismissed by old guard because it didn't fit the dogma. But, this is the way the process works. So, man, when these guys die off, we'll, but until they die off, we're going to have this problem. And what I didn't count on was Newton resented it so much. And he resented Hooke, because Hooke was the guy who brought him in. It's like, I invite you to a party, and then we all make fun of you. And Newton was not thick-skinned. And so Newton turned around and said, right, you don't like that? I am never publishing anything with you again. And not only that, I'm going to be silent until I have everything. And so Newton ended up publishing these big tomes. He put one on mechanics and one on optics. And it's not all right. A lot of it in there is wrong. But the amazing thing is, so much of it is right. And so much of it is still in use today. Like, these are diagrams from his book. And if you look in our book, these diagrams are basically there. It's like phenomenal. Equations that he wrote down, we write down exactly the way he wrote them down. The guy was amazing. As I say, 10 years on physics, phenomenal progress. 10 years on alchemy, 10 years on spiritualism. And then he actually became much more outward going towards the end of his life. He became the master of the Royal Mint and was instrumental in catching some forgers. Well, actually, I think so. So what I've noticed is, as I get older, my frontal lobe is closing down. So whereas before, I've noticed that in my interaction in class, for example, I tell stories for longer. And there's part of me knows, just get on with it. They're not that interested. Look, they're all looking at their phones. And there's another part of me going, they should hear this. This is golden, they'll remember this. And so there's this, your frontal lobe is, of course, modifies your behavior. It's your regulator, it's your management system, and it closes down. You tend to lose your inhibitions. My daughter will walk 5 yards away from me, and, why is she walking 5 yards away from me? Because she's slightly embarrassed, because I'm likely just to wave to people and go, hi, pleased to meet you, and all that kind of stuff, rather than being reserved. And 5 years ago, I would have been much more reserved. So maybe that's what happened to him, where he became more outward-going because his frontal lobe was closing down. And he was becoming the batty old guy. But 350 years ago, basically we talk about him all the way through Physics 1. We're going to talk about him all the way through Physics 2. This guy's amazing. Guy's absolutely amazing. You can go onto this thing called the Gutenberg Press, and you can get his actual book for free, actually. And just look at it and just be amazed. You can see him struggling for the language. When you're at the forefront, there's no language to describe what you're seeing. And so part of it is trying to find the word. And it's up to you to coin the word, but you're kind of like, you're thinking, is there a word I can use? And then eventually you go, no, there's not, and you coin the word. So it's kind of history. I tell you, there's a whole area, history of science. It's a difficult area to get into because the historians don't have the science, and the science people don't have the historical expertise, the being a historian. But I think it's fascinating for those who get into it. It's
What colors does it have?
so okay. Moving on. So we have reflection. Have you ever noticed the difference between a mirror and a satin finished aluminum fascia? In one case, you can see yourself, and in the other case, you can't see yourself. But it's both made out of aluminum. The only difference is the smoothness of the surface. So if you have a planar surface, then if you like, the integrity of the approaching light will be maintained. The spatial integrity will be maintained. So what's on the left stays on the left, what's on the right stays on the right. If you have a rough surface, then the integrity of the incident light is not maintained. Everything is jumbled, and you lose the image information. Same amount of light is reflected. It's the same stuff. It's just we lose our image information. We called one is specular, one is diffuse, or we call it in modern parlance a mirror finish or a satin finish, basically. When you look at that either on the large scale or on the small scale, if you were to look at just one ray of light, so now let's talk about that. If you've ever seen the Superman comics, and they have Superman with X-ray vision, and they kind of show the X-ray vision like that, like it's coming out of Superman's eyes, that's a common misconception that somehow you perceive, you see. These are detectors. They're not senders. So you receive light. So we have a source of light and we have a detector of light. And the light goes in straight lines. So I see that blackboard because light comes on and then is reflected into my eye. If you were to do this experiment, and you will do this experiment actually, we can do it like Newton did it, where we put the mirror down on a piece of paper and we use a couple of pins. We didn't have light source, he didn't have a laser or anything, he had a couple of pins. And then he looked into the mirror and he saw what appeared to be these pins back here. And he lined up a couple more pins. And then he drew these axes and he measured the angle to the normal. And he found that the angle of incidence equals the angle of reflection. Second thing, he realized that the incident ray, the reflected ray, and the surface normal are all on the same piece of paper. They're all on the same plane. Because otherwise, I could have something where this comes in along the x-axis and it bounces off along the z-axis. And that would also be angle of incidence equals angle of reflection. But that's not what light does. If you're coming in along the x-axis, you go off along the x-axis. You don't turn a corner. So two laws, really. For specular reflection, the angle of incidence equals the angle of reflection, and the incident ray, the reflected ray, and the surface normal are all in the same plane. He measured the angles with respect to the surface normal, and that's our tradition. There's nothing saying we have to do it that way, but he measured it that way, and we do the same thing. The equations will not work if you use the other angle. Well, once they get a bit more complicated. For incident and reflection it works, but not once we get to refraction. Okay, so we know about reflection as much as we need to. What about a thing called refraction? Refraction is the bending of light when the light goes from one medium to another. So when we get light going from air to water, or from air to diamond, or back again, diamond to air, we get what appears to be a bending of light. If you look at a fish tank, and you look at the corner of the fish tank, you'll often see two fish that seem to be doing synchronized dancing. And it turns out they're the same fish. We're just looking that way and seeing the fish, looking that way and seeing the fish. So there's a bending of the light. where does that come from? That comes from actually a slowing of the light inside the medium. So we can characterize transparent mediums with a figure of merit called a refractive index. And basically the refractive index value n is the speed of light in vacuum divided by the speed of light in the medium. There's nothing faster than the speed of light in a vacuum, so the numbers are always a big number divided by a little number, so they should always be bigger than 1. The way we can represent that is we say, well, the frequency of the light doesn't change, but the colour can change. And so the way I can get a lower speed is I take shorter steps. Frequency is like your cadence, how quickly you step. The wavelength is like how big your stride is. You can slow down by simply taking shorter steps. I remember one time I was at a sales meeting and I saw somebody, I didn't know their name, I couldn't remember it. I was going to be embarrassed if I saw them, so I decided to just go behind them. But I didn't want to make it obvious I was veering behind them. So what I did was I kept walking, but I just started taking shorter steps. And so they went in front of me and I missed them. What a crazy, messed up psychology that is. But, you know, a bit of science is really useful sometimes. I'll just take shorter steps. I'll decrease my wavelength and I will go slower, but not appear to go slower.
You measure as you walk in?
No, I just deliberately took smaller steps. Okay. So as light travels from one medium to another, the frequency does not change because that's the colour, but the wavelength does change, and we can define the refractive index now in terms of, well, the wavelength in the vacuum. So n equals c over v, the speed in the vacuum, divided by the speed in the medium. Well, that's equivalent to saying the wavelength in the vacuum divided by the wavelength in the medium. That's an important equation. We're going to come back to that in a little bit, so watch out for that. And that leads us to probably one of the most important laws that we're going to deal with, which is Snell's law, which basically says that the refractive index of medium 1 times the angle of incidence in 1 is equal to the refractive index in medium 2 times the angle of refraction in medium 2. Okay? So that's what we got there. Snell's law. I'm going to stop now because, yeah. Oh, just to show you, we have refractive indices of some common materials. They're always going to be bigger than 1. Air is just slightly bigger than 1. Diamond is 2.4. Really slows light down. Means we get big angular effects, big dispersion effects for the colours of light. So it looks very bright and reflective, depending on how it's caught. Which medium does light travel fastest in? It travels fastest in the thing with the smallest refractive index. So this is fastest, and this is slowest. I'm just looking at my clock. I don't want to run out of time. Refractive index is 2. What is the speed of the medium? N is equal to C over V. So V is equal to C over N, which equals 3 times 10 to the 8 over 2. So V equals 1.5 times 10 to the 8 meters per second. So that's that guy. And which medium does light have a longer wavelength? It has a longer wavelength in the thing it's going fastest in. So this is long R lambda. This is short lambda. Whoops. And I'm going to stop it there.